morning, everybody. My name is Brodie Popovic. This is Cosmology / Dark Energy from home, and I'm going to talk about SN1A cosmology. But to start, I think it's worth talking about hauntology. Jacques Derrida defines hauntology as the nostalgia of lost futures, the haunting of the present by the past. For me, as an American, this sort of burnt-out Pizza Hut, I think, is a really good example of that, and across literature, time, space, there are other great examples. One that comes to mind for me is Absalom, Absalom by William Faulkner. He talks about, the haunting of the American South by the Civil War and how this affects the people, and it's this very much conflicting narratives and these ghosts that still live with everybody. And you might be wondering why we're talking about ghosts that still live with everybody for a Cosmology from Home or a Dark Energy from Home conference. And I think that's a fair question. And going back to this idea of the haunting of the present by the past, this is something that really struck us recently for Dark Energy and the Dark Energy Survey. So those of you that are watching in a dark room, get ready. The screen is about to turn very bright as we talk about Dovekie and recalibrating SNe 1A. So the reason I'm talking about hauntology is because of the night sky and our calibration attempts. So I have plotted here the night sky with a bunch of tertiary stars that we use in all of our SN1A samples, PS1, SNLS, CSP, DES, etc., etc. And the problem with this is we need all of these Type Ia supernova and all of these stars to train our models that we use for cosmology. And here's the issue, is that all of these surveys are not only separated by space, but they're separated by time as well. So we've switched to just the CalSpec stars, which we use as our primary standards for calibrating across telescopes, and in a perfect world, every CalSpec star would be directly observed. But you could see here on the bottom this timeline that CFA3K finished taking data in 2009, followed by SDSS, CFA3S, SNLS, CSP, PS1, DES. And so a lot of these, like CFA3 for instance, the telescope simply no longer exists. And for CFA3 in particular, I believe that someone took out one of the V-bands for CFA and shot it with a shotgun in the backyard when they were done. Should give you maybe a bit of an idea about how fun calibration can be sometimes. So I bring up hauntology because we can't abandon these samples. CFA3 in particular contains a whole bunch of spectral sequences of Type Ia supernova that are absolutely necessary for training our model, SALT. The spectral adaptive light curve template. And so we throw in a bunch of spectra and photometry into SALT. It trains a model that we can then use to fit distances and move on to cosmology. So we're somewhat constrained by what we're doing and the amount of data that we can use and what to do. And so that kind of impacted us for the Dark Energy Survey and our initial cosmology results. And so we spent a bunch of time going back and recalibrating everything, which I will briefly talk about here before moving on to Dark Energy and the status of today. So we started the Dovekie calibration project a while ago, and so the goal is to ensure uniform brightness across all Type Ia surveys. You can imagine that any kind of miscalibration between our low-redshift telescopes, CFA3, CSP, CFA4, for instance, and the high-redshift telescopes could be degenerate with cosmology. So we want to make sure that we get these exactly correct. So Dovekie takes place in broadly 3 steps. We have our filter characterization, our cross-calibration, and our distance measurements. For the filter calibration, which I will briefly go over here, but we're not going to get into too much detail, we use Pan-STARRS AP aperture photometry and Gaia spectra to ensure agreement between data and filters. So we have these two independent sources, the All-Sky Pan-STARRS survey and Gaia, and we compare our filters that we have from our various surveys to the Pan-STARRS aperture photometry and combined with CalSpec spectra, and then direct observations of those same stars with Pan-STARRS and Gaia and whatever telescope we want to cross-calibrate, and we can figure out how good and how well calibrated all of our filters are. Once we've done that, we move to cross-calibration. So we again combine that Pan-STARRS aperture photometry along with some novel DA white dwarfs from Boyd 25, and we use both of these at the same time to simultaneously calibrate all of our desired surveys. And then we use distance measurements with our novel salt surface that I was talking about, and we want to assess the impact on cosmology. And all of this is available at the GitHub, github.com/bap37/Dovekie. So that brings us to the cross-calibration. So we have determined how good our filters are in the previous step. And so with this fixed, we'd like to have the same observed magnitudes across all of our systems. So we have what hopefully is recognizable as a color magnitude diagram. On the bottom is the Pan-STARRS G-I color, and well, that's the x-axis, and the y-axis is the Pan-STARRS R minus DES R. And so there's a lot of data points, and we have our data, the slope of our data in a black solid line, and the synthetic spectra that we use two libraries, CalSpec and STIS NGSL v2, and those are shown in dashed and dot dashed lines. So, this looks like a whole bunch of noise, and that's because right now this is uncalibrated data, and what we would like for it to look like is this. And this sounds really simple, especially when you only have one survey or two surveys, but we have a lot more than that. We have DES, SDSS, PS1, Foundation, CFA3, CFA4, CSP, SNLS. We've additionally added SWOPE and Atlas. And, you want to do all of these at the same time. So that leads us to the impact on cosmology. And so this is where the original Dovekie paper ended. We had a very rough delta W as an assessment, and when we finished, we looked at our delta W, and it was a little scary. It was about 0.1, and this was with a very rough estimate, no bias corrections, no full cosmology pipeline, just taking distances, very rough distances, and subtracting them versus the old distances. And that was a little worrying because 0.1 is quite a big shift. That's about 5 sigma outside of anything you'd expect. And so we didn't really trust this number. And that led us to say, okay, let's actually go in and do this properly. So we all, of course, remember 2024, the DESI results. And so we have them here, the DESI BAO combined with DES 5-year and CMB and all those various combinations. And this placed the tension with lambda CDM with this CPL W0 WA derivation at about 4.2 sigma, I believe. And so I've worked on DES 5-year, I've worked on Pantheon Plus, and if I had to choose one that I wanted to work on again, it would be DES 5-year. No offense to Pantheon Plus, but I prefer having to only deal with one survey rather than go back and work on the 18 surveys again that constituted Pantheon Plus. So we decided, working on Dovekie, well, we have what hints at a pretty strong, hints at a cosmological tension, and we have this newly recalibrated salt surface and offsets. Why not go ahead and try to redo DES 5-year? And so this took place in broadly 4 steps. One, it's been about 2 years at this point, since the original DES 5-year supernova analysis had completed. So we wanted to make sure that any changes we were seeing were actually changes from our calibration, not just from the pipeline itself changing. SNe, which is the program that we use, has been constantly updated. It is a living program over the last 2 years. And when we were doing that, we actually did find some issues. And we'll talk about that. That's number 2, the Fitzpatrick 99 color law. So we wanted to address that, capture that, and then we went on to update our calibration and redo the entire cosmological analysis. So what we have here is the recreated DES 5-year results. So the blue is the original values for W0, WA. Orange is our attempts to recreate this. And we have our recreated plot here, showing W0, WA space. So it's not exactly the same. We used a different fitting program. However, I would say this is like a 1/6 of a sigma, and I was pretty happy with this. But this isn't exactly what happened first. What happened first is we were having a whole bunch of issues actually getting the right values. Our W0, WAs were off fairly consistently, and we couldn't figure out why compared to the original DES 5-year analysis. And after learning a lot of very crazy sorting algorithms to kind of go through the last 2 years of history, we found this issue. So we have wavelength plotted on the x-axis and delta mag plotted on the y-axis. And what was found out by Dr. Stephen Thorpe, right now at Cambridge, is that the Fitzpatrick 99 color law we were using in SNe was an approximation. A very good approximation, so long as you were focused at an RV of 3.1, but as you moved away from an RV of 3.1, it became progressively worse. And you can see all of the RV values plotted here, and at an RV of 1 especially, you can see this gets really off. And so the reason we didn't notice this earlier is it is entirely self-consistent, and it turns out not to have impacted any of our results too much, but we did implement this, fold this in, and make sure we used this increased precision F99 law, because the way we model color for Type Ia supernova and dust and RV now allows for non-RV of 3.1 values. So if we redo the entire analysis using this new F99 law, we get this. So here's the change from the original to the new version, and as you can see, like I said, nothing crazy, which is good. That is pretty comforting that we weren't too far off. So moving on, what we have here is the difference in 0 points from the original fragilistic calibration and Dovekie as a function of the median redshift, just to visualize it, and for each of our filters. And so you can see that the low Z filters, specifically CFA3, CFA4, CSP, those are all within 1 sigma. This is good, but you also notice the error bars on those are about twice as big as everything else, and again, we can't get rid of these yet. They just have too much valuable information for the SALT training that we are constantly haunted by these ghosts. But you can see Foundation and DES have changed quite a bit. The G-I color and G-R color for both of them is noticeably different, and we wanted to figure out what this is going to mean. And a quick shout out again to Benjamin Boyd and the DA White Dwarf Network. Those are what is responsible for those really tight error bars in DES compared to everything else. DES did have these DA White dwarves and direct observations of them. So this brings us to the distances. We went through the entire cosmology pipeline. We passed all of our blinding checks. We did all of this good stuff, and we wanted to compare our distances directly. So we have, as a function of redshift, the original DES distances minus our new Dovekie DES distances. And for the SN heads out there, we've provided just the raw distances, the bias correction values, and the total delta mu. For those people that are a little less into SN cosmology, it's these white points that are interesting, these white points that are important. And this gives us the DES-Dovekie distance diagram. a Hubble diagram. And here we have the distance modulus mu, redshift, and this gives us about 5 to 10 fewer supernovae than we had in the original DES 5-year. That's not unexpected. We changed the calibration, we changed the SALT model, but it's good that we have a similar amount. And this brings us to our systematic uncertainty. So we have sorted these into various categories: contamination, survey modeling, redshift, calibration, Milky Way, SN1A astrophysics. The important thing to note here is the single biggest individual systematic is still SALT3 plus calibration. However, the biggest family of systematics is the SN1A astrophysics family, which takes up about 30 to 40% of our total systematic uncertainty budget. And we actually do a little better in our calibration, and indeed overall systematic uncertainty. We notice about 10% smaller compared to the original DES 5-year. So when we look at this in flat ΛCDM space, we move from an omega matter of 0.352 to 0.33. This brings us more in line with all of the other surveys for Type Ia supernova, which is neat. In WCDM space, we get negative 0.986 plus or minus 0.02. It's consistent with LCDM. That's good. And in W0WA space, we get these new values, which, if we plot compared to the original DES 5-year, leave us at 3.2 sigma compared to the original 4.2 sigma. And so you can see that, we've shifted. Most of this shift comes in the W0 space. So, I think an important question is, where does this leave us? Going back to almost where it all started, I was alerted to this W0WA CDM discrepancy at the L'Encontres de Montréal and in 2024, about 2 years ago almost. And so this is a screenshot from the DESI collaboration at the L'Encontres de Montréal last month, the most recent one. And we can see that what we started with, 3 different SN1A samples, all pointing at different lambda CDM discrepancies between the work that I've done and the reanalysis work of Pantheon Plus by Taylor Hoyt, and also the work that David Rubin has done on Unity. Now all of the different SN1A systematics and samples all point to about 3.4, 3.2 sigma. So they're all very consistent, but are on the edge of detection. And this is also the case, as people have begun to show, that CMB plus BAO is also pointing to about 3.23 sigma away from lambda CDM. So we're seeing this really broad agreement that all of these independent probes are all pointing ever so slightly away from lambda CDM. And so where does that leave us in supernova and plans for the future? Because that's really what I'm best at talking about. There are a bunch of projects in the works. We have Pastry, which is a desk project for DES. I know, confusing. But Rebecca Chen is leading an entirely host photo Z analysis for DES, which is expected to unlock a bunch more new supernova and provide a new method that can be used for LSST. Having not quite tackled calibration, but done some calibration, I'm going back to my true love, dust, because that is our single biggest group of systematics. My graduate student, Nicholas Shamtanis, is working on a DES analysis of hostless 1A supernova, which will be quite interesting. And in the more immediate cosmology future, I think, there are new low-redshift samples. The DBAS sample, done by Maria Acevedo and Nora Sherman, are leading a DE-CAM-only analysis with 400 new Type Ia supernova. And Atlas, which I hope everyone has heard about, mostly led by Jack Tweddle, UK Murakami, and Eli Marlin, have over 3,000 cosmologically usable Type Ia supernova that they plan to use as a low redshift anchor. And this is sort of the end of my time. I'm seeing 1950. And so I would like to thank everybody for coming, and I'm happy to answer questions when the time comes.